Hello everyone, welcome in this third lecture in the NPTEL course on Riemannian geometry. So today I am going to continue with this discussion of the sum angle property. Today we'll look at the sum angle property on general curved surfaces. So let me remind you that earlier in the first lecture we saw this generalization of the sum angle property or an analog of the sum angle property for spheres, right. So if A1, A2, A3 is a triangle on a sphere of radius r with, let us say, external angles epsilon 1, epsilon 2, epsilon 3. So remember, what did we mean by triangle? By a triangle we just meant that there are three vertices and then the edges are given by shortest paths on the sphere connecting the two the vertices. Then the analog of the sum angle property is that the sum of the external angles plus a correction term which is given by the area of the triangle divided by r squared gives you 2 pi, okay. And I also explained that you should think of this correction term as the total curvature contained inside this triangle, right, because one should think of 1 by r squared as sort of the curvature of the sphere and then multiplied by the area, so that is the total curvature contained inside the sphere. So today in today's lecture I first want to make sense of what curvature really is, okay. Alright, so let us draw a picture. So I am going to restrict attention to parametric surfaces in R3, okay. Alright, so here is a picture. You have the parameter space where I will use coordinates u and v. You have an open set and then you have a surface sitting inside R3 which I am going to denote by n. So the 2 just indicates that this is a 2-dimensional object, and so you have this map R so that any point on your surface in R3 can be parametrized by a point with coordinates u comma v in the uv plane, okay. So essentially just intuitively what do you how do you think of curvature, right? So of course if you take a flat plane lying inside R2, then any sensible definition of curvature would mean that the flat plane has 0 curvature, right, because you do not see it actually curving, so it should have 0 curvature. On the other hand, if one sort of distinguishing feature of a plane is that if you look at the normal vector, let us say the unit normal vector along the plane, then that actually remains constant, right. So no matter where you are on the plane, the unit normal vector will always remain the same. So intuitively, so the intuition should be that that curvature is essentially, or at least captures, the rate of change of the unit normal vector, okay. So let us try to make this intuition more precise. So let us introduce some notation. So let this be a domain D and let R be a surjective map from D to M. So you are parametrizing points on M using this function R. So let this be a parametric surface. Okay, and let us take a point P given by R of some u comma v, right. So then the tangent space to your surface at the point P, so let us say your point P is somewhere here, the tangent space is going to be spanned by these two vectors which I will denote by Ru and Rv, okay. So this is going to be the span of Ru and Rv at the point u comma v, where what is Ru and what is Rv? Well, those are the partial derivatives of r in the u and the v direction. Right, so these partial derivatives give you tangent vectors at that point r of u comma v, and then the tangent space is just a span of these two. So if that is the case, then what will be the normal vector? So normal vector should be perpendicular to both these basis tangent vectors. So given two vectors in R3, how do you construct a vector that is perpendicular to both? You of course take their cross product, right. So then define the unit normal vector to be I will call this n at u comma v. So that is precisely going to be the cross product of Ru and Rv, and of course this cross product may not be a unit vector, so you need to divide by the norm. Okay, so let me make a couple of remarks. First is that I am dividing by something, so I better ensure that something is not 0. So we work with regular surfaces, so which means that this cross product is never 0, right. So at each point a unit normal vector is well defined. Also there is a choice in the unit normal vector, right. So instead of taking Ru cross Rv, I could have just as well taken Rv cross Ru and then divided by that norm. So that would basically give me another normal vector which is equal but opposite in direction to the n that I have written down, right. So by writing down the normal vector in this form, I am actually making a choice, okay. So I am making a choice of what normal vector I want. Okay, so here is the first sort of basic claim. So as I said earlier, our intuition is that the rate of change of the unit normal vector should somehow capture what the curvature of that surface is, right. So let us differentiate the unit normal vector. So the claim is the following. So if x is a vector field on M, then if you differentiate the normal vector in the direction of x, that is always going to be perpendicular to the normal vector. In particular, this implies that this is always going to be in the tangent space to M, right, because in R3 there are only 3 directions. You either have at any point on M, you either have the tangent space or you have the direction, essentially the unique direction up to sine, which is perpendicular to the tangent space. So if something is perpendicular to that normal vector, then it ought to lie in the tangent space, right. So that is what this implication says. Okay, so let us quickly prove this. The proof is very similar, conceptually at least, to the proof that if you have an arc parametrized curve, then the acceleration vector is always perpendicular to the velocity vector. This is something we saw in the previous lecture. So this proof is also similar. You use the fact that the norm squared of the normal vector is always 1. So now if you differentiate the norm squared, by the way, before that I should I should point out that when I write this, this is basically the component wise derivative. So in multivariable calculus we learn how to calculate directional derivatives of functions. This n can be thought of as essentially three functions, right? The components along the x direction, the component along the y direction, the component along the z direction. So when I write dxn, I basically calculate this is the vector that is obtained by calculating the directional derivative of each component of n, right? Okay, so so if I differentiate the norm squared, then again by the product rule, this is basically going to be just 2 times the inner product of what you get when you differentiate the normal vector, the inner product with the normal vector. On the other hand, because norm squared of n is 1, this is going to be identically 0. So that means that this is perpendicular to n, okay. So next I have this simple sort of observation that if you take this map where you assign any vector, let us say you fix a point P, you take a vector in the tangent space at that point and map it to this the directional derivative of n in the direction of that tangent vector x. Our claim has shown that this will also belong to the tangent spaces at M. So that means that this assignment actually gives you a linear transformation from, and the observation is that this is a linear map in X, right. So if you take a linear combination of vectors here, the directional derivative basically is the linear combination of the directional derivatives of the original vectors, right. So this is a linear map, so it gives you an endomorphism of the tangent space at that point, okay. So that brings me to the next definition. The shape operator of M at P is defined to be the linear map SP which goes from the tangent space of M at P to itself, and SP of X is precisely this map, okay. So that is called the shape operator, and then the curvature of my surface. So this is called the Gauss curvature in honor of Gauss, who worked extensively on this in the sort of early part of the 19th century. The Gauss curvature of M at P so it's usually denoted by K. So K of P is simply the determinant of this map. So any linear transformation has many invariants associated to it, namely the trace or the determinant or even the other sort of symmetric products. So the Gauss curvature is defined to be the trace, to be the determinant of the shape operator, okay. You might ask, of course this is a linear transformation between a 2-dimensional vector space to itself, so it has essentially 2 invariants, either the trace or the determinant. So you might ask, why not the trace? So it turns out that the trace, actually the sign of the trace depends on the choice of the normal vector that we have made, because if you made the other choice of the normal vector which is equal and opposite to this n, the shape operator would get changed by a sign, by -1. So that of course affects the trace, but it does not affect the determinant. So the determinant is actually independent. So the Gauss curvature is independent of the choice of the normal vector that you made, okay. So that's one advantage of looking at the determinant, okay. So now how do you compute the Gauss curvature? So So computing the Gauss curvature, right. So here we take motivation from some elementary linear algebra. So linear algebra aside, so let T be a linear transformation which is symmetric or self-adjoint. Sorry, let me before this I needed to state one fact. Right. So the next sort of observation, I'll write that as a claim. Is that this SP is actually symmetric or self-adjoint. Okay, what does that mean? That means that if you take the inner product of SP of x comma y, then that's the same as the inner product of x comma SP of y. So let me quickly give you a proof of this. So by definition, what is the inner product of SP of x and y? Well, the shape operator is precisely the derivative of the normal vector in the x direction, but then by the product rule, this is precisely the directional derivative of the inner product of ny in the x direction minus n times the derivative of y in the x direction. Okay. All right, but what is this? This guy is always 0 because n and y are always orthogonal to each other, right? N is the normal vector to the surface. So this is just going to be n times the directional derivative of y in the direction of x. Now just reverse the roles of x and y. So because the inner product is symmetric, reversing the role of x and y would give you something like this, right. So now what is the difference? So this implies that the difference in the two quantities that I am interested in is basically the inner product of n with dy of x minus dx of y. Okay. But what is this difference? It's an elementary calculation that this difference is precisely the Lie bracket of the vector fields x and y. So I hope you have seen Lie brackets in the smooth manifolds course. If not, I'll actually maybe quickly review the Lie bracket couple of lectures from now. But in any case, the point is that that the Lie bracket is again something that lies in the tangent space. So now if you take the inner product with n, this is going to be 0. Okay, so this completes the proof of the fact that the shape operator is symmetric. Right. So now how do you actually compute this quantity k? So remember, k was the determinant of the shape operator. So how do you calculate determinants, right? So this is a little linear algebra aside. So suppose T is a self-adjoint or symmetric linear map, right? Then we know by our diagonalizability criteria that one can choose a basis of eigenvectors. So then there exists orthonormal basis of eigenvectors with eigenvalues eigenvectors, let's say E1 and E2 with eigenvalues, let's say lambda 1 and lambda 2, right? But what is really this lambda 1 and lambda 2? There is a so-called min-max principle, where lambda 1 is precisely given by so if you assume that lambda 1 is the smaller of the two eigenvalues, this is precisely given by the minimum of TV inner product with V divided by norm V squared over all non-zero vectors in R2. Similarly, lambda 2 is actually given by the maximum okay, and then of course the determinant of T is given by the product, okay. So as long as I can calculate these two quantities, the determinant will just be the product of these two. So I now apply this to the shape operator, okay, in the following way. So let gamma from some minus epsilon to m be smooth arc length parametrized such that gamma of 0 is p and the velocity vector is some tangent vector x at p, okay. So then as before, let T of s be the velocity vector. So this is going to be a unit vector. So just to draw a picture again quickly, so this is my surface, this is let's say the point P I am looking at, and this curve gamma is in let's say it's this curve in red, and I have a tangent vector at this point. Now I somehow want to do the same thing that I did in the plane. I want to rotate this in an anti-clockwise direction in the tangent plane at P. So I also have the tangent plane here. So in the tangent plane, I would like to rotate this to get this vector n of s, and then I of course also have this normal vector small n of s at this point, right? Okay, so how do I define this capital N of s? So let capital N of s be the unique vector unique tangent vector to m at gamma of s such that this combination of T of S, N of S and this little n of S forms an oriented basis for R3. So these are three orthogonal vectors, in fact orthonormal vectors. So here my notation is that n of S is basically the normal vector to the surface at gamma of S. Okay. So what do I mean when I say that these form an oriented basis? So i.e. if you take the cross product of T of S and N of S, that will be of course pointing in the direction to the normal of this to the surface, and I want this component to be positive. Okay. So that is what I mean by when I say that these three form an oriented basis. So now again, as before, because the speed is constant, this implies that the acceleration vector is perpendicular to the tangent vector, which means that this is a basis of R3. There is no component of the tangent vector along T of S. So that means that the acceleration vector can be written as some kg of S, some component along capital N of S and some component along small n of S. So this component is called the geodesic curvature of gamma at gamma of S, and this little component here is called the normal curvature. Okay. Okay, then I have the following claim that so remember with my linear algebra aside, we have to, in order to calculate the eigenvalues, we have to compute these sorts of inner products and then take the min and max, right. So for the shape operator, an easy calculation, so remember x was this tangent vector at gamma dot of S. So it turns out that this actually just computes the normal curvature. Okay, let us quickly write down the proof. So or maybe in the interest of time I will leave the proof as an exercise. Okay, so essentially maybe let me give you a hint. So the hint is the following. So if right, so the hint is to come up with the following formula, that if you take n of S and calculate the derivative at S equals 0, then that is precisely going to be dx of n. Okay. So if you assume this this formula, then so assuming this, I will leave the proof of this as an exercise. So assuming this, one can complete the proof of the claim, because what is Sp of x comma x, that is just dx of n comma x, which by my hint here is d by ds at S equals 0 of n of S times gamma dot of S evaluated at S equals 0, right. right. So for that, so let me maybe since this is a new page, let me write down that equality again. This is equal to okay, but then by the product rule, because n and gamma dot are always orthogonal, by the product rule, by this trick that we have used often, this is the same as minus n of s times gamma dot of s at s equals 0. But by definition this is precisely minus the normal curvature at 0. So whatever I wrote is off by a sign. So there should be a minus sign here. Okay. So that completes the proof. So a consequence of this is that that if I put k1 of p to be the minimum of the normal curvature of all such curves passing through the point P, and similarly if I put k2 of p to be the maximum with a sign, yeah, let us forget about the sign does not matter because eventually I am going to take the determinant. So then the Gauss curvature is precisely the product of these two. Okay, so these two things are called the principal curvatures. Okay, so let me maybe give you a few examples and then I can state the local Gauss-Bonnet, and that will be the end of this lecture. So let me quickly sort of give you a few examples. So just to give you a feel for what this Gauss curvature looks like. So let us first look at the two-dimensional sphere. Okay, so here it's a very good exercise to show that that each of these sort of normal each of these principal curvatures is going to be 1 by r. So k1 is going to be 1 by r, k2 is going to be 1 by r. In fact, the shape operator is basically going to be a diagonal matrix with entries 1 by r and 1 by r, which means that the Gauss curvature is precisely going to be 1 by r squared. So we have gone through all this effort to define the Gauss curvature, and we have eventually ended up with a number that seems reasonable, right. So I argued in the first lecture that 1 by r squared should in some sense be thought of as the as the curvature, or at least some quantity which depends inversely on r. And here we our definition of Gauss curvature yields exactly 1 by r squared as the Gauss curvature of the sphere. Second, I take the example of this cylinder. Okay, so this is the cylinder, the set of points x, y, z in R3 such that x squared plus y squared is, let us say, 1. Okay. So now suppose you are at this point, you can think of two, so essentially to calculate the principal curvatures you have to compute the minimum and maximum normal curvature. So you can think of two types of curves. You can firstly think of a curve that is essentially this circle, right, that is the circular cross section of the cylinder, or you can think of a curve that goes in this vertical direction. Now in the vertical direction you see that the normal vector as you move in the vertical direction, so if you look at the normal vector which is pointing out here, as you move in the vertical direction the normal vector is not going to change. So the derivative of the normal vector in that direction is going to be 0. On the other hand, the derivative of the normal vector along this circle is going to be something positive or at least something non-zero. But because one of these directions gives you 0, and you can check that for any other directions the normal vector is going to vary with the same sign as the sign that you get when you look at this circle. But because the Gauss curvature involves a product of these two quantities, the Gauss curvature on a cylinder is actually 0. So even though to the naked eye the cylinder actually seems sort of curved, but if for instance you are an ant on this surface, intrinsically you will not notice any curvature. So the Gauss curvature of a cylinder is actually 0, and in fact later on we will see that this actually is a manifestation of the following elementary observation, that if you cut a cylinder along this vertical along one of the vertical lines and unroll the cylinder, the distances between 2 points will actually remain unchanged. So in a way the cylinder is actually isometric minus this vertical line. As long as you cut along this vertical line, it is actually isometric to the plane, and later on we will see that isometries preserve curvature. So it is no surprise that the cylinder has 0 curvature. Okay, let me do one more example and then I will state the theorem, the main theorem, and stop. So this is we saw positive curvature in the sphere, we saw 0 curvature namely for the cylinder. So what does negative curvature look like? So a prototypical example of negative curvature is this thing called as the horse saddle. Okay, so you should think of this to be the head of the horse and this to be sort of the tail of the horse. So whenever somebody is riding a horse, you put the saddle on, which roughly has this shape. So this is the prototypical example of negative curvature. Why is this negatively curved? Because if you take a curve that goes in this direction, you see the tangent vector is moving towards the normal, right? On the other hand, if you move along this curve, then the tangent vector is actually moving away from the normal, or I mean depending on your convention. So let us actually take the normal vector to be, let us say, this vector. Then if you traverse along the red path, you are actually moving away from the normal vector. So that would give you a negative principal curvature. On the other hand, if you are traversing along the blue path, you are actually moving towards the normal vector, so that would give you a positive principal curvature. So when you multiply them together, the Gauss curvature would be negative at this point P. Okay. So this is the prototypical example of a negatively curved thing. Okay, so finally let me state the main property, namely the main theorem, the Gauss-Bonnet theorem for curved surfaces in R3. Okay. So let P be a polygon. The definition of the polygon is the same as before. Let P be a polygon contained inside M with exterior angles, again with the proper sign convention, epsilon 1 up to epsilon n. Then if you calculate the sum of the external angles, add a contribution that comes from the geodesic curvature of the edges, and add the total curvature contained in the interior of the polygon, then that ought to be 2 pi. Okay. So, so this is the generalization of the sum angle property to arbitrary surfaces in R3. So, of course, I have not given you any proofs, I have not proved this local Gauss-Bonnet, and in fact it is quite a non-trivial theorem, but I hope I have conveyed some sort of intuition for curvature and how that affects your local geometry in terms of sum of angles, properties of triangles and so on. So, my aim in these 3 lectures was to convey some form of intuition for curvature. Starting, I mean in the next three lectures I'll quickly review what some basic theory about smooth manifolds that I'm sure you must have seen in a course on smooth manifolds, and then after that I'll actually introduce what Riemannian metrics are, and then from there on what curvature etc. is. So basically let me just give you a brief outline of the course from here on. So the first part, after the review of smooth manifolds is over, the first part is going to be about Riemannian metrics and curvature. Then I am going to move to metric geometry aspects of Riemannian manifolds. At the end of this first part, I hope to actually state the Gauss-Bonnet theorem precisely. Notice that I referred to these exterior angles, but I never actually defined them precisely. So at the end of the first part, I hope to precisely define what all these quantities are and then give a proof of the Gauss-Bonnet theorem. In the second part, we will talk about metric geometry aspects of Riemannian manifolds. So namely distance functions and how that affects the curvature, and how in turn the distance function is affected by the curvature and so on. And then in the last part, if time permits, which I am not very optimistic, but if time permits, then we will talk a little bit about comparison geometry, right. So some more advanced topics in Riemannian geometry. So anyway, so that's it for today. Next class we will start our 3 lecture review of smooth manifolds. Alright, so thank you for your attention, and I will see you next time.